Okay, so here we're going to get into some proper big O notation discussion. So I talked about it last time, and I honestly don't think it would have been a good idea to introduce that alongside metrics. We should pace this out a little bit because these are all important concepts that we're going to be using all the time. So we'll try to do it right. So here's the idea. We are trying to we're going to try to get control of a lot of concepts in numerical analysis, distances, with respect to certain quantities. So like I said before, this could include, say, the order of a polynomial. It could include the spacing of sample points. It could include, say, for interpolation. It could include widths of rectangles for quadrature. What else would we use it for? A number of operations they have to do in order to, say, get close to an optimal value of, say, quadratic polynomial, using what we are going to call the gradient descent method. And so, so this is this is going to end up being a really important concept. And so we're going to talk about things like big O of the width, which is generally going to be denoted as h, rectangles. Using, say, left-hand rule for integration, that's going to be, say, big O of h. If we use the midpoint rule, then it would be big O of h squared. And if it's the, say, Simpson's rule, it's going to be big O of h to the fourth. And as h gets really, really small, basically what we're going to say is that these quantities are going to be shrinking roughly like h, or h squared, or h cubed, or h to the fourth, etc. So what is big O notation? We should go ahead and talk about that. So big O notation is basically, you have a comparison of two different functions. You have a function f and a function g. And you would like to say that g is bigger than f in some fashion. And so big O notation basically says that as x goes to some limit, say a or infinity, that the absolute value of f of x is going to be less than some constant times the absolute value of g of x. What this constant is usually neglected. We usually don't compute that. Sometimes it's really horrible and it's important, but oftentimes there's not much you can do to find it. But what is important is a quantity that's independent of x. And so what you can do then is you can sort of neglect it. You can just say the absolute value of f of x is less than or equal to c times the absolute value of g of x. But then instead of saying all of that, we'll just say f is big O of f of x is big O of g of x as x goes to a. So then if g of x goes to 0, f of x goes to 0. And that's going to be the main use of that. Or at the very least, we know that f isn't going to get bigger than g by some scaling. So they basically behave, so g basically dominates f as it goes to 0. Now there's other kinds of O notations. We have little o notation, where basically we have, we take a look at, we say f of x is little o of g of x, as x goes to a, if it turns out that when I divide f by g and I take the absolute value, that that quantity goes to 0. Now this is really important when we talk about things like derivatives. So you can actually frame the definition of a derivative in terms of little o notation. And I'll show you how to do that in the lecture. And then there's a last one, which is theta notation. And you say f is theta of g of x. If what you can say is that f is big O of g of x and g is big O of f of x. What this really means is that these two quantities are roughly the same in the limit, except for maybe by scaling. So an example of that sort of thing would be as if you take a look at the function g of x is equal to 1, so just constant function going off to infinity, and the function f of x is equal to x plus 1 over x minus 1. And then we know as x goes to infinity, that goes to 1. Or if even I can have, like, say, 2x minus 1 on the top over x plus 1, and then that quantity go to 2. Both of those, all three of those would be, say, theta of each other, if you like. And it basically says that in the limit that they all behave roughly the same. And in this case, they would all behave like constant functions. They wouldn't be truly constant functions, except for the g of x. But in the limit, after a long time, the difference between them and a constant function would be negligible. So that's the idea of that. In any case, so we'll go into the lecture, and I'll talk about all three of those different ideas and give you a bunch of examples of how they're used. And then after this, we can go and start talking about polynomial approximation properly. All right, it's been great discussing this with you, but let's actually get to the lecture. All right, so let's go ahead and get started. So we're talking about three big things, and so we have big O notation, we have little o notation, and we have theta notation. Okay. So big O, little o, and theta. So I'm going to go ahead and give you definitions and run through an example out of numerical analysis for each one. So big O notation. So we're going to suppose we're going to let f go from R to R and G from R to R, maybe smaller domains depending on the context. And we say that f is big O of G, so call this definition. Say f of x and g of x, as x goes to a, if we have absolute value of f of x is less than or equal to c times the absolute value of g of x for some c. Okay. So some pretty easy examples. You can see as x goes to infinity, we know that the absolute value of x squared plus 2x is big O of, say, x squared. How do we know that? Well, we have the triangle inequality, and so I'll just put a proof. So we have, and actually we don't need absolute values here, so we'll just say x squared plus 2x is big O of x squared, and then we just, in the investigation of big O, we put absolute values. So we have x squared plus 2x in absolute value. This is less than or equal to x squared plus 2 absolute x by the triangle inequality. Now we know that if x is bigger than 1, and so if I put 1 here and we know, say, x is bigger than 1, here we're thinking as x goes to infinity, so we can have it as big as we want, then this is going to be less than or equal to, say, x squared plus 2 absolute value of x squared, and so we just write x squared there, and this itself is equal to 3x squared absolute value. So thus we have x squared plus 2x is in absolute value is less than or equal to 3 absolute value of x squared. And so, which means that x squared plus 2x is big O of x squared. Right, not too bad. Let's see. Another example. I don't know, just gotta come up with something. Here's an easy one. Say, oh, is that easy? I don't know if that's so easy or not. Oh, but yeah, okay, we do this. Yeah, that's not bad. So, as x goes to 0, we have that x squared is equal to big O of x. So, how do we prove this? Well, it's not too bad. So the absolute value of x, we can, you can think of it as being absolute value of x times 1. And as x goes to 0, we can think of, so as x goes to 0, we'll just say for absolute value of x less than 1, we have, and we can stay less than 1 as much as we like, the absolute value of x times 1, if you replace 1 with x, then it actually shrinks. So this becomes less than or equal to absolute value of x squared. And hence, x squared is equal to the little of x, where that constant is 1. All right, not bad. So just think of this graphically. You have 1 coming over here, and the absolute value of that is going to give you this, or x, rather, x to 1. And then x squared is here, like this. So in this neighborhood, x is always bigger than x squared. Okay. So, not too bad. Let's look at something a little bit more sophisticated. Okay, so here I want to talk to you about sort of the first taste of proper numerical analysis. So we're going to start off with a function f whose derivative is actually a continuous function. That means that we're later going to be able to use, say, the extreme value theorem. So what are we actually trying to do? Well, we want to get an estimate on the integral from 0 to 1 of f of x dx, and we're going to use the left-hand rule. So left-hand rule is given by this, and so basically you chop up in a whole bunch of equal chunks of size 1 over n, and you choose the leftmost point as your sample point that goes into f. And so basically what you get is that the difference, written this way, is actually going to be big O of 1 over n. Okay, so let's go ahead and take a look. So let's go ahead and prove that. So proof. Okay, so what we're going to do is we're going to write these two quantities, the integral and the sum, in two different ways. I'm going to write the integral as the sum, and I'm going to write the sum as the sum of integrals. So let's go ahead and do that. So, I'm just going to say write. So we're going to take this integral, 0 to 1, of f of x dx, and I'm going to write it as the sum of n equals 0 to capital N minus 1 of the integral from n over capital N to n plus 1 over capital N of f of x dx. Okay? And on the other hand, I'm going to write the sum of n equals 0 to n minus 1 of 1 over capital N of f of n over capital N. I'm going to turn this into a sum of integrals. So I'm going to write it as the integral from n over capital N to n plus 1 over capital N. And inside the integral, I'm going to put this constant function
f of n over capital N dx. So this is really just the constant I moved in here, and I just converted this guy into the integral of into this integral of 1, and then afterwards I can shift this in, and that's fine. Okay, so now we're going to take a look at the difference between these two guys, and it gives you something interesting. And so I'm going to write like this. So I have, we have this, so we're going to write this difference, and let's call this difference star. And so I'm going to write star as the sum of n equals 0 to n minus 1 of the integral from n over capital N to n plus 1 over capital N of f of x minus f of n over capital N. And we're going to take a look at this dx. Okay, so the next thing I'm going to do is I'm going to use the fact that this is differentiable, and I'm going to use the mean value theorem. And so that tells me that there is some c sub n for each one of these intervals, such that we get this. So we have the integral from n over capital N, n plus 1 over capital N, and then we get f prime of c times x minus n over capital N. And this is done by dx. Okay, so a few things to note. F prime is continuous. So by the extreme value theorem, there exists an m bigger than 0 such that we have the absolute value of f prime of x is less than m for all x in, say, 0, 1. All right, so that's a good start. Now, since x and n over n both live in this interval of n over n to n plus 1 over n, this tells us that the absolute value of x over n minus n itself is less than or equal to 1 over capital N. Okay, so now if I call this star star, we find that then star star in absolute value is going to be less than or equal to the sum of n equals 0 to infinity, crashing through by triangle inequality, or not n infinity, to n minus 1, then we're going to get this. That derivative is bounded by m. That difference is bounded by 1 over n. And what's left is we have n over capital N to n plus 1 over capital N dx. And that we know is 1 over n. So it's sum of n equals 0 to n minus 1. M times 1 over n squared. Now if we add all these together, this is just a constant sequence, then that is just going to be n times m times 1 over n squared, and so ultimately we get m over n. Well, that, my friends, is exactly what we were saying. So we have the difference, star, in absolute value, then is less than or equal to m times 1 over n, and so then that tells us that star, which was this quantity if you remember, that star is big O of 1 over n. So yeah, so that's numerical analysis for you. And more or less, that's how all of numerical analysis works. Generally speaking, for anything involving, like, say, calculus, like integrals and derivatives and whatnot, the mean value theorem is going to come up a lot. And it also comes up a lot in, say, polynomial approximation. And so we'll see that in the next lecture when I talk about Taylor series. But okay. Cool. So that's big O notation. Let's take a look at little o notation. All right. So little o notation, we say that f of x is little o of g of x as x goes to, say, some quantity a, if absolute value of f of x over g of x is goes to 0, or just goes to 0 as x goes to a. Okay, turns out that little o notation implies big O notation. Sorry, little o notation. Just little o, let's be more specific, and this is going to be, say, a homework problem. F of x, be more precise, sorry. F of x is equal to little o of g of x implies that f of x is equal to big O of g of x, right? That's actually not going to be too hard to demonstrate. All you have to do really is to show that the ratio is less than a constant at some point, and then you just multiply over g of x. And that's everything. So here's an example. All right. Ln of x is little o of x to the n for all n. All right. So let's go ahead and take a look at that. So our goal is to show, and we can even take it up a notch and take it just from n. I will say it is little o of x to the r for all r greater than 0. So not just integers, but any power of x. All right. So our goal is to show that ln of x divided by x to the r in absolute value goes to 0. It doesn't actually have to be an absolute value. If you go to 0, you go to 0. And so we can do that using Hopital's rule for all x r, and I should say as x goes to infinity. Do we use Hopital's rule? No, probably not, right? Okay, so all we need to do here is just show this with Hopital's rule. Let's say by Hopital, ln of x divided by x to the r is equal to the derivative of the two. So the limit as x goes to infinity is equal to the limit as x goes to infinity of 1 over x divided by r times x to the r minus 1. Okay, and so that gives us the limit as x goes to infinity of 1 over r times x to the r, and this goes to 0. And so then there we go. Let's see. I mean, I think that's a pretty good example to start off with. Let's do a more calculus-driven example. And basically we're going to say that, all right, so let's take a look at sine of x over x minus 1. We'll say that this is little o of x. Okay, so let's go ahead and take a look. Probably the easiest way to see this is if I go ahead and replace sine of x with its power series. So sum n equals 0 to infinity of -1 to the n, x to the n over 2n plus 1 factorial. And this is going to be, say, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus etc. So then I see that sine of x divided by x is going to be 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus etc. And then finally, sine of x over x minus 1 is equal to x cubed over 3 factorial plus x to the 5th over 5 factorial minus etc. I should have a minus sign there. And I should say as x goes to 0 for this little notation. Okay, so now let's go ahead and take a look. So my claim is that if I divide this by x, sine of x over x minus 1 divided by x should go to 0. Well, what is this? This is going to be minus x squared over 3 factorial plus x to the 4th over 5 factorial minus etc. And this is equal to say x squared times something else, minus 1 over 3 factorial plus x squared over 5 factorial minus etc. So this is convergent. And this term is going to 0. And so we win. In fact, sorry, all this is over x, all this is over x. And so, no, actually, that was fine. Yeah, so then rather, this is just going to 0. And yeah, that gives us everything that we wanted. And in fact, you can even see that I could have taken out 2 x's. And so, really, this is sine of x over x minus 1 is little o of x squared. All right, and so that's not too bad. A lot of times when you get this sort of little o notation, this is going to be coming from a Taylor series. And in fact, the definition of a derivative can be defined this way. And so, for instance, we say that f of x is differentiable at x equals a if there exists an a and r such that this quantity f of x minus f of a minus a times h is little o of h as h goes to 0. Pretty sure that's right? So if I divide by h. Yep, that's the idea. Okay, so this is, say, you can write this as a definition. In terms of little o notation, this gives you differentiability. And in fact, you can use this version of the derivative to demonstrate derivatives of functions of multiple variables. And so if you replace a with, say, the gradient at a point, so that'll give you the derivative of a multivariable function. And then you can even ask what the derivative of something like a gradient is, which would be a matrix, and etc. And so we say that A is equal to f prime of A. So yeah, okay, cool. All right, so let's wrap this up and talk about theta notation. So theta notation is basically this. F of x is equal to theta of g of x if f of x is equal to big O of g of x, and g of x is equal to big O of f of x. Say as x goes to some quantity a. Right. So let's go ahead and just give a quick example. So let's compare the sequences x plus 2 over x minus 1, or we'll consider these functions, say f of x, and we'll say take a look at g of x, and this is say 5x over 2x minus 1, right? Essentially what we need to show is that f of x is big O of g of x, and g of x is big O of f of x. So one way to do that is to just take the ratio. So f of x over g of x, what is that going to give us? So we have x plus 2 divided by x minus 1 times 2x minus 1 over 5x. If I divide top and bottom by, say, x squared, I guess. Let's see what we're going to get. So we have x over 2 minus 1 times 2x minus 1 over 5x. And then I'm going to divide by 1 over x squared and 1 over x squared. Right, so I'm not really changing anything. That's just a fancy way of writing 1. So I'm going to take one of these x's, I'm going to put it here. I'm going to take another one of these x's, and I'm going to put it here. And ultimately, what do I get? So I get 1 plus 2 over x on the top. On the bottom, I get 1 minus 1 over x times 2 minus 1 over x divided by 5, right? Now as x goes to infinity, this term, and this term all go to 0. And so we'll just put an arrow here. So as x goes to infinity, we get 1 over 1 times 2 over 5, and so we get 2/5. So, so then what I can say is, now we don't know if maybe as we're going to 2/5, maybe we jump over it or not, or something like that, but we know in the limit, we're always going to be in some sort of neighborhood of it. So if I just bump it up a little bit, and just instead of writing 2/5, I just say, I put a bound on this guy of f of x over g of x. We know eventually it's going to be less than 1. Otherwise, it wouldn't converge to 2/5. So then it tells us the absolute value of f of x is less than g of x. And so then that tells us that f of x is equal to big O of g of x. And symmetrically, we can do the same argument. And by the same argument, we have g of x is equal to big O of f of x, and thus f of x is equal to theta of g of x, and vice versa. Okay, that's nice. All right, now let's take a look at one more example. And it's going to be more or less the same thing. So here, I'm going to let f of x is equal to the square root of 1 plus x squared. And g of x be equal to 1, just x. Okay, This is a hyperbola, depending on how well you remember your calculus, or your pre-calculus. But basically, we're taking a look at these two functions. And we're saying that, in the end, they're roughly the same function. So, let's take a look. So, first we need to just, it's the same sort of argument I just did. So if we take a look at absolute value of f of x over g of x, it's going to be equal to the square root of 1 plus x squared, it's a positive quantity, and over x. And so I'm trying to show that f of x is equal to theta of g of x as x goes to infinity, by the way. All right, so what does this give me? Well, I can rewrite x as square root of x squared, and I can write it like this. So I have 1 plus x squared over x squared, and then we get the square root of 1 over x squared plus 1. And as x goes to 0, this goes to the square root of 1, which is just 1. All right. Again, without more reasoning, we can't be sure that it's always going to stay below 1, but we can definitely say that if this is going to 1, then this ratio itself has to be eventually less than 2. So, for a large enough n, for a large enough x. Thus, we have the absolute value of f of x is equal to theta of g of x, or in other words, we have the square root of 1 plus x squared. Well, actually, what we demonstrated here is equal to big O of g of x, but symmetrically, we have, oh my god, that's such a big eraser. We have g of x is equal to big O of f of x. And so thus, 1 square root of 1 plus x squared is theta of x. Okay, good. All right, so I'll stop it here, and this is 3 examples of this is 3 different sort of asymptotic notations that are handy when we're talking about numerical analysis. And so next time we'll get into proper numerical analysis beyond just the one example I just gave you with integrals, where we actually talk about polynomial approximation. All right, thanks for listening, and I'll see you back in a while.
Okay, so that's it. That is big O notation, the little O notation, and theta notation. And all of those are used all throughout mathematics, analysis at least, and especially anytime anybody wants to talk about asymptotic quantities. It's used in computer science too. If you look at the Bible of computer science, this is The Art of Computer Programming by Donald Knuth. This is the book that they used to use until basically everybody got scared away from it. But it has a tremendous section here on just mathematical notation, etc. And for a long time, people just use this as a Bible. It does everything in assembly language, but you can convert all these algorithms later. Honestly, this wouldn't even make a terrible numerical analysis book itself. But maybe more of a computational combinatorics book would be better. This would be better suited for that class. But if we go through here and we talk about analysis of algorithms, we can see that he has a whole section here on the O notation, right over here. And this is basically how he quantifies, all sorts of things. So here he actually has what's called the harmonic series and convergence, or rather, not really convergence. But basically, you can talk about how close the sum of 1 over n gets to being, say, the natural log of n, with some odd constant. And maybe as a bonus lecture, we can go ahead and just talk about that at some point, because that's an interesting idea. In any case, so this big O notation is used all over the place, and yeah, it's a really convenient way of expressing convergence and distance without explicitly mentioning the constants. I guess, yeah. So I think I'm going to leave it there, and I'll see you next time.